In this lecture we will discuss about one-dimensional autoencoder. That means input is basically one-dimensional data, and then we are trying to make a stacked autoencoder to compress this particular high-dimensional data to a low dimensions. So these are basically the modules which we are importing in this particular program, where we are using TensorFlow, using Keras to develop the models, NumPy for numerical computation, Matplotlib for plotting data, and etc. So here we are basically just printing the TensorFlow and the Keras version. Then we are loading the data from MNIST dataset, MNIST fashion dataset. So this particular line, so we are basically capturing the data. Then this particular data has been broken into multiple parts. One section for training data, this tuple is for training data and training level, and this tuple is for test data and test level. So in this line we are basically printing the training data type and training data shape. So during data pre-processing we are normalizing, because this MNIST fashion dataset basically image and its pixel value starting from 0 to 255, we want to make within 0 to 1 normalize. That's why we just loaded by 255. Then the class names which are present there, which you can find out from the MNIST dataset fashion database. So first of all we are plotting the first example, what particular data is there in the training class. Then we are converting all the datas, that means from two, because the datas are 2 dimensions image, we are trying to make a demonstration for one-dimensional autoencoder. So the data, 2-dimensional data, first of all we are converting to 1 dimensions. Actually we just flattening the datas. How is it? This is basically shape, train data shape. It is basically a sample number by a 2-dimensional array size. So the train data we are reshaping of the sample numbers by this 2-dimensional data we are making as 1 dimension. That means for each image now it is not in 28 by 28 form, it is now in a long vector form. That means 28 into 28 number of elements. Similarly we are reshaping the test data similar way. Now we are creating the one-dimensional stacked autoencoder, that input data of 28 by 28 dimensional data now feeding to a layer of 128 number of nodes. Then it is converted to 32 number of nodes. That is a compressed data dimensions 32, that is, and then again it is compressing to 8 dimensions. So stack is basically coming like this: initially 28 cross 28, then 128, then 32, then 8. So this is the final layer. It is a final encoded data dimension. So now we are creating two sequential models, a stacked encoder 1-dimensional and stacked decoder 1-dimensional, because as you know that for autoencoder the first section is basically encoder and the second section is decoder. So in the encoder part we are adding 3 dense layers, one for 128, second for 32, and final for 8. So for the first input, first 128 number of units, we have to specify the input shape, because we are directly feeding the input to this particular layer. That's why this is additional thing, only it comes to the first layer first interface layer, and all the activations we are using the ReLU activations. Then the decoder part. So in the decoder part we have to start from 32, because 8 is the output is 8 of output dimension for the encoder is 8, so we have to so that particular output will first take an interface to the decoder side as a 32 units, then 128, then the original image data 28 cross 28. So that's the start decoder 1D. We are using second layer dimension is 32, then first layer dimension 128 we are producing back, and then final is the 28 by 28, then the original input. And the final layer activation function is sigmoid, and all the internal activation functions are hidden layer activation functions are ReLU. Now we are forming a stacked encoder, one dimensional encoder. This is a sequential model, it's a sequential object, so it takes an argument, first encoder then decoder. Now we are printing the stacked encoder one dimensional summary. That means what are the layers are there inside this stacked encoder one dimensional encoder and decoder part, that will be printed. Then we are forming the encoder model itself. Input data equals to input layer. We are taking this from Keras models, Keras layers. So this is input layer, and the input is basically we have to provide the data dimension, individual data dimension. This is 28 by 28 into 28 instead of 28 by 28. That would be for 2 dimension. Now in encoder we are creating the encoder model. That is a model input data, then the encoder model is only stacked encoder one dimension, that means encoder part, and it takes an argument, that is the input data is a input to this stacked encoder one dimensional model. Then we are basically printing the encoder summary. Now this is a compilation stacked encoder. This is a complete stacked encoder autoencoder. Its compilations using binary cross entropy and Adam optimizations. We could have different Keras optimization SGDs, trust rate descent with the learning rate specification. Then the training process, complete stacked autoencoder one dimension. Fit is a function for training this particular autoencoder. This is the data, training data, and output should be compared with the data itself. So instead of label we have to provide the data. 100 epochs, batch size 32, you can change, shuffle is true, validation split means within the trained data 20% will be kept for validations. So now we can just change it a little bit, plus let's set 10 and let it be a little bigger. So now these are the plot functions for imaging individual sections. In individual image data we will plot, and there is something which are intermediate data dimensions will be plotting, and all these things are basically plotting the sample data, etc. Let me run this code first. So it will run. So it started running. So out of 10 epochs it has run only 5 epochs. This is the training loss, this is the validation loss. Okay, so this is the training loss curve, blue one. This is the validation loss curve, orange. Yes. And these are the input datas, and these are reproduced after decoding. This is input data, this is decoded data. and these are intermediate 8-dimensional feature distribution for each of the inputs.